Okay, welcome everybody to the Monday SITP colloquium. Today we are very happy to have Jorge Kurchan from ENS Paris, and he will be telling us about an unexpected bridge between black holes and glasses. Please go ahead.
Hello. Okay, thank you very much. Yes, this is the plan of what I hope I can do. So first I'm going to go very quickly, a brief reminder of SYK model and why reparametrization invariance that appears there is important. I assume that most of you know and are much more familiar with black holes and such than I am, but I need to present this just as a frame for what's coming afterwards. Then I will rush you through the classical glass phenomenology and the mean field glass theory, which includes Parisi replicas, of which I'm sure you heard speak, and dynamics and glassy dynamics. And next, I will show you how reparametrization appeared in glassy dynamics, very much like the one you know, those of you who are familiar with SYK. It is essentially the same one. And the softness that appears, that emerges, is physically relevant and also measurable in the case of glasses, and has I will give you some interpretation. Uh, and then at the end, I will tell you that for every glass you give me, I can construct formally for you a strange liquid or metal if it has fermions. By strange liquid, I mean something whose excitations are not simply either quasi-particles or easily numberable, numerable, and they are just very different from one another. And time permitting, just for amusement, I will show you how when you put in contact two glasses, you get a wormhole through them, by which I mean that the coupling between two glasses actually reproduces the phase diagram that you get when you couple two SYK models. And in the case of glasses, you can interpret this in a different way. Okay, so just these are my two references because it's a very readable review of glasses that is light, and if you want to have a look at that, is the one here I'm showing you. And I am following this paper we did with these people, which is in ConMat, and one that I posted very recently. Okay, so this is the part where I am going very quickly through just to set the stage, SYK model. So as you know, it is a system with some number of interaction of some disordered interaction of some number of fermions. In the present version, it's Majorana fermions, but that's not crucial at all, but it makes everything easier. And the JI, JKL, or have the appropriate symmetries, and they are random. It's a mean field model in the language of us, the Glassy people, because it's fully connected. Every I, J, and K, L, they are being considered. And it's a model of strange metal. Metal means gapless, and strange means lots of excitations quite unrelated from one another. And in this case, in most cases, entropy, zero temperature entropy. So what do we do? As you know, we calculate the partition function, and we compute the average. If we were, we should calculate the average of the log, but it turns out that for this model, calculating the average of the log and the log of the average happens to coincide. So we can get away with calculating simply the average of the partition function, which is good because it saves us some headaches. And once we do this, we can do this in the usual way of being glass people or by summing diagrams. Whatever you do, you end up with an equation for the two-point function. And it's remarkable that the mean field parameter, the non-fluctuating quantity, is a two-time quantity, which is something that is unusual if you think of magnetism, where the mean field, there is only one parameter, which is the magnetization, a one-point function, but it is quite familiar from DIA. It's an approximation for turbulence, spin glass dynamics, of which much more afterwards, dynamical mean field theory of electrons, and replicas, as you will see. So you solve this thing, and in Euclidean time, because you're calculating the partition function, and oops. And what you discover is that you get a decay of the correlation, which becomes extremely slow. It has a power law, which is cut off at some point that depends on the inverse temperature. And the more you go down in temperature, the more relevant this little piece becomes. And what happens is that you get a region where you really have slow dynamics. Because you have slow dynamics, a posteriori, you discover that this time derivative is, in a sense, negligible. At any rate, it is small. And once this happens, if you completely neglect it, you get a reparametrization invariance like so. So that the only term that breaks this reparametrization invariant is the time derivative, and it's small. So I like this little picture, which is a Mexican hat that has been slightly tilted. You have a symmetry that is slightly explicitly broken, and the lower you go in temperature, the more straight this hat is. So you expect that, like in any model of this kind, you will have not quite a zero mode, but a very soft one. And for this one, you would like to make a theory. Like when you construct any sigma model in any case in your lives, you don't want to study, or you don't want to, at a first approach, to study the hard directions, and you want a theory for the flattish ones. And this was constructed, and here you have it. It's what you call the Schwarzian model, which is the effective theory, which would be like moving along this bottom of the hat, which is slightly tilted. So the fact that you have derivatives here tells you that reparametrizations are not completely for free. They cost a little bit, and that little bit is the effective theory. And then people tell me that this structure is reminiscent, for a number of reasons, to black holes. The very fact of having a reparametrization quasi-invariance, the remarkable fact discovered by Kitaev that the Lyapunov exponent of the system saturates a bound, which, first of all, it's not very common that systems do saturate that bound, and it's expected from systems that are also models of black holes. So this was seen that this model might be a metaphor for this kind of situation. There is also T going to zero entropy, meaning that yes, if you make first the thermodynamic limit and afterwards let T to zero, you have a finite entropy. And all this makes the system like a toy model of black hole. And the relation of having started with Majoranas and ended up with a theory for the soft modes is a kind of, how shall I say, again, metaphor of CFT-ADS. Okay, having said this, let's go to glasses. So what do I mean by glasses? So two types of glasses that are popular. One is you have a lattice with interactions between spins who are living at the vertices. Some interactions are antiferromagnetic and some are ferromagnetic. So the spin has to decide what is better to do because it doesn't want to be parallel this one to this one, but it does want to be parallel with this one, and this creates a complicated situation. And so that the landscape of possibilities for the spins is very complicated, very rugged, and the system takes a long, long time to discover which is the best. Another one that is easier to understand, much more common is, and this is a real one, spheres. For example, this is a colloid in water. So these are little spheres that are in water. And if they don't crystallize, they form a glass. So they don't find their way to the best situation, and their dynamics get slower and slower, a bit like when you have coffee, a ground coffee in a pot, and you start tapping it so that it goes down so that you can add more coffee in your pot. And this is a complex situation for all the little constituents, and this creates slow dynamics. So the simplest of the simplest conceptually would be, okay, I'm going to do hard spheres to make it easy in d dimensions. And this, if I can avoid crystallization, it's okay. It's a perfectly good glass. It has slow dynamics. It has a very complex landscapes with many possibilities, with a very rugged or at least very disconnected space. Now, nobody can solve this. So one thing you can do is let the dimension go to infinity. And this we know how to solve. We know how to solve completely the dynamics of a system of hard spheres in the limit of infinite dimensions. It's been relatively recent, surprisingly enough, that this has been achieved.
Sorry, George, I have a completely naive question. So in this classical model, when you say solve, what are we trying to solve for? It's just the configuration of the spheres or what?
So you first, and your situation is very similar to SYK. You would like to solve for something. Then you make the approximations and you discover who is the order parameter in which everything is expressed, in terms of which everything expressed. In this case, it is two-time correlation functions, just like in SYK, remarkably. So what is a two-time correlation function? It tells you how much a density profile, a mass profile, let's say, in the liquid is changing in time. And in
Okay.
infinite dimensions, this measure of how the density profile evolves is exactly expressible in terms of two-point functions, which are the non-fluctuating quantities.
Okay, so it's the density two-point function of these spheres.
Exactly. It turns out that with this, you have everything you need. Just
Okay,
like in
thanks.
SYK, it turns out, and you only realize when you do the calculation. Okay, but so there is a little interesting thing that happens, which is all in all, this one is a tough one, but people realized or guessed years ago, uh, 30 years ago maybe, that if you made a model like the one we were discussing before, but this time the etas are bosons. They are just ordinary numbers living on a sphere because bosons are unbounded, so we have to bound them somehow. And so the easiest is to bound them on a sphere. And the J's are symmetric random couplings, just like SYK, only that's symmetric. This thing here, if Q is greater than 2, uh, has the same phenomenology of spheres in infinite dimensions. It's a remarkable fact. And so I drew it this way. This is the landscape. Don't ever ask me what the axes are. Probably this one, this is the energy, and the x-axis is something. It's just all your variables. So this thing happens to have the same phenomenology, the same transitions, the same qualitative features as hard spheres or even soft spheres in infinite dimensions, which is the best we can do relatively close to real life. And here already a historical analogy. Just like I guess people who saw SYK said, I don't see the black hole here. These are J's and these are Majorana fermions. People, when this was suggested, said, where are the particles here? And there are no particles that you can see here. Well, it turns out that the maths of this is an easy version of actually hard spheres or soft spheres in large dimension. So we will concentrate on this one. Okay, so what do you do when you have a system like that? Well, there are three strategies basically. The first one is to calculate the partition function. Now, turns out that you have to calculate actually the average of the logarithm of the partition function, because otherwise you don't get the right result. If you calculate the average of the partition function, very rare configurations having a very small probability will dominate, and in most cases, you do not get the right result. So this was noticed by Sam Edwards and Phil Anderson long ago for spin glasses, and there you're forced to do something about it. Calculating the average of a log is notoriously difficult. So what they came up with was to calculate powers, 1, 2, 3, 4, and then for every power, and then do the analytic continuation to n0. And when you have a 0 here, then this is the log essentially. So if you can continue analytically to near n equals 0, you have the log, and this is what is called the replica trick. Now, the replica trick is, as you will see in a minute, it's quite strange. It's so strange that the way it is applied, that for many years, lots of people didn't believe in these applications. At any rate, the way to carry it through in mean field was devised by Parisi, and now we know that his solution is correct in mean field. Now we know, meaning that the mathematicians have written unreadable articles that prove it. Many years later. Okay, that's strategy number one. And what do we get with this strategy? We get the configurations that you see here in red, which dominate the equilibrium measure. They have to be low so that e to the minus beta, the red things, is still sizable. Okay, the other possibility, which is much more physical, but at the beginning it was thought not to be doable, was to do the dynamics in contact with a bar. So you launch your system from a random configuration and you let it go, essentially gradient descent with a little bit of noise. And this mimics the contact of the system with a thermal bar. And now what you want to calculate is the dynamics of the system. So things depend on time. And as you will see, you discover, again, this is your question, Raghu, you discover that two time correlation functions are the good mean field non-fluctuating parameters. It so happens. And then there's a third strategy, which is simply to count states. This is count valleys at a given level. This takes you very close to Morse theory and the constructions for Morse theory. The reason I am mentioning it is that it's going to take us the closest to the constructions of SYK and quantum mechanics. The way we count valleys it will bring us very close formally to SYK. Why? The reason is that you can prove that if you want to calculate the number of valleys that you have at a certain level, what you have to do is add all the periodic orbits, the periodic trajectories of a certain time life, a time of return, and this gives you the number that you get, gives you with their probabilities, and this you can prove gives you the number of valleys that you have. It takes maybe half an hour in a blackboard to convince yourself, but it's something you can prove. So counting dynamics, but forcing the orbits to close after a time t gives you as a result, with the same path integral, gives you as a result the number of valleys you have of lifetime t, the period that you force. This third strategy is the one that, as I say, will take us closer to SYK. So quickly, the Parisi ansatz for reference. So you have your spins, which, sorry, they were called eta in the last transparency. I notice now that they're called S here. These are the ones that live on a sphere. You want the overlap, SI, and A and B are the names of the replicas. You have n replicas. So these, the full set of parameters when you're calculating this is a matrix of little n by little n, n being the power that appears here and which we want to take to 0. So now we have a matrix whose real dimension is going to end up by being 0 because that's what we need to calculate a logarithm. And we have to invent a set of matrices that whose structure we can sort of continue analytically, which is a bit optimistic wording because this is not really an analytic continuation. It's a kind of a dream of a continuation. So for example, this was the solution devised by Parisi. You break your matrix in blocks of sizes, let's say x1, these are the big ones. And then you are allowed to break each block into sub-blocks of a smaller size x2. Of course, these have to divide n. N must be an integer because that's the only way that I can understand a matrix. And then the values that I can attribute to QAB are some value in these places, some value in the pink places, and some other value in the brown places, and another value in the diagonal. So now I write the saddle point equation of my whole thing, and it looks like this. So you notice the similarity with SYK, only that I'm not integrating over time, I'm summing over replica indices. Now I have to take this matrix of some dimension with some x1, with some x2, and some n, plug it in here, and then I write what are the necessary values of Q1, Q2, Q0, X1, X2, etc. that can satisfy this equation. And here comes the step that is difficult to swallow the first time you hear it. You prolong analytically, or you prolong, let's say, this thing for n going to 0, x1 staying finite, but not necessarily integer, x2 becoming larger than x1, real and finite. Both of them are larger than n, in spite of the fact that they were born smaller than n. And this solution, once you've decided that you will attribute reals to the values, is the one that gives you the solution when n goes to 0, x1, x2, q1, q2, q0, you find a solution. So as you see, it is, now we understand this much better, but when it first appeared, it does seem quite bizarre the first time you hear it. Notice, once again, the order parameter is a 2-point function, 2-point being two replicas. Instead of being the two things, the two vectors at different times, as in SYK, they are at different replica indices. Okay. Now, this
Sorry,
other
George.
approach. Yes.
What were P and Z in the previous?
Oh, sorry. P is just what you usually call Q in SYK, is the order of the number of spins. So it was 4 in here. Sorry, here. Here it's called Q, and here it's P. Okay, so it's simply the order of the interaction. And what else?
The Z, the Z.
This one?
No, in the equation.
Is there a z here?
In the QAC multiplying that.
So yes, QAB, QBC, QAC, these are the replica indices. So you are multiplying the matrix whose elements are raised to the p minus 1 power, just like in SYK
No,
with
no.
time.
The
Yes.
coefficient of QAC is Z there, right? The Z in the second term in that.
Oh, sorry. Yes, sorry. It's a mass term that is there to keep the spherical constraint that all the S's live on a sphere.
Ah,
Because
okay.
if you
Okay.
don't have that, because they're bosons, you need to keep them put. If not, they
Okay.
go
It's
to.
like a Lagrange multiplier.
It is exactly a
Okay.
Lagrange multiplier.
Okay. Thank you.
Good.
Is this
Sorry?
quantitatively correct or just qualitatively correct?
No, it is exact. This now we know that this gives you the exact result. Only that, depending on the model, you might sometimes have to put little blocks into the little blocks and little blocks into the little blocks and so on and so forth. But yes, it is exact. It's not even an approximation.
Sorry, can you remind me again, if you don't mind, how the hard sphere problem became a spins on a sphere problem?
It didn't. What happens is that it so happens that the phenomenology we know now, the kind of equations you end up with, these have the same, let's say, kind of solution as the hard spheres. Actually, the story is exactly the other way around. Somebody guessed that this was a model for particle systems, and it was a contested fact because you don't see any particles here. But for example, when one solves the dynamic equation of these, and you can also do something with replicas, one finds that one gets very much the same situation qualitatively, the same kind of equations as with this one.
I see. So this was found numerically or by doing analytic calculations?
All this is, you can check numerically, but is doable analytically.
I see, thank you. And sorry?
Yes, numerically what we do, or not me, but what other people do is go from dimension 12 to dimension 2 in the spheres and see how things change.
I see. Thank you. And the matrix solution with QAB, it is quantitative for the spins on a sphere problem.
Yes, and for the original problem for which it was set, which was sharing to Kirkpatrick, what we don't know is in finite dimensions if this scheme, we don't know of any case where we can apply it exactly and know exactly.
Okay. And one more question I had, if you don't mind, was what was the interpretation of keeping x2 greater than x1 greater than n in the limit n going to 0?
It was a guess.
It was a guess.
It was a guess, and then at the very end, it turns out that x1 and x2 have a probabilistic interpretation. But at the very, very end. So you have 3 papers later, you realize.
Okay, thank you. Okay.
Okay, so dynamics is much more, if you want, less bizarre in the sense that you start with a Langevin equation. Sorry, the S's became etas again, they're bosons, so you have a gradient descent term. You have a dynamic Lagrange multiplier, as Raghu was saying, and you have noise. Noise is to attribute a temperature to the bath. The variance of the noise is 2 times the temperature. And we make the noise white, although this is not crucial. I am going to call temperature Ts for stochastic because this is not going to be the quantum temperature we will talk about later. So this is very much like what you do in an experiment. And now this thing, you can treat it really exactly like you treat SYK, very much the same way. But you have to remember that now you have 3 order parameters because you have the noise and you have the fields. So you have the field-field correlation, the noise-field correlation, and the noise-noise correlation. Noise-noise correlation is going to be trivial throughout what I'm going to say, but instead of having one G as you have in SYK, think of it as 3 different Gs. just like when you have colors, let's say, in SYK. So the only thing is that R has an important physical interpretation. If this is a correlation that tells you how much the system moves, this is a response that tells you how much the system responds to a kick. You see, you put a noise at a time and you see what happens at a later time. So this is a response function. And you put this in the machine, calculate the diagrams that you have to calculate, and using the very, very same methods as in SYK, you end up in these equations. Because D is trivial, it doesn't play a role in these equations, but you see that these equations, if you look at them from very far away, they look very much like the SYK equations. Lambda is the Lagrange multiplier now for some reason. So you recognize the delta here that you have in SYK. So it's a couple of equations, but I hope that you're convinced that they are very much of the same kind. And now we can solve. It actually turns out that we can solve these equations for long times. We cannot solve them exactly. Exactly, we can put them in the computer. What we can do, and it's quite a surprise, is that you can solve for long times. And you can solve it exactly, the asymptote for long times, and they are non-trivial. And this is what I'm going to describe to you. So I'm going to do simultaneously how this solution looks like and how the physics of real life looks like, because to a certain extent, this is a good model for this situation in real life of a particle going down. So what happens is something rather surprising. You're at low temperatures and you start at a time t star and you see how the correlation decays. This tells you how the system moves. And then you wait for a longer time and you see how it decays. And it takes longer. I mean, the first part, no, it reproduces very well, but then it takes longer. And then you wait for a longer time and it takes even longer. And then you wait for a longer time and it takes even longer. And this process never stops. So this means that the system is moving slower and slower and slower and slower as time passes. But except for this first fall to a plateau. But the actual, this process never stops. Or to be more precise, it stops at times that diverge with the system size. And if you look at the response, or rather the integral of the response, which is a better quantity, you see the same thing. It goes up quickly at the beginning, and when the system is older, and you then apply something, it moves up at a slower rate and at a slower rate and so on and so forth. So this process where the system, what this is telling you is the system is not equilibrating ever. And it's telling you it's what it's called aging. This is what you get from these equations directly, but you get also in real life. So much so, I have it here. This is very much a plastic ruler, which you are compressing. At the beginning, the compression, this is this curve, is universal. This is the fast compression that you get like in sound waves. And then it creeps to a new length. And here you see aging times, and here you see 0.03 days up to 1,000 days. And the rhythm at which it creeps continues to evolve up to here, you see 3 years. So that if you give me a plastic ruler, by doing this experiment, I can tell you when it was made from molten plastic. But what is amazing is that these mean field equations are doing the job of reproducing this kind of thing. Okay, and here comes a surprise. It turns out that these equations, as you can see from here, begin to move, as I told you, slower and slower in a certain regime. So for the reasons that people who do SYK will recognize very easily, you can neglect these red things. More or less, you can neglect them exactly to the extent that you can neglect them in SYK. Meaning, yes, they are becoming small, but be careful because you need to choose a reparametrization, which is a good one. So exactly by the same reasons, for the same reasons, and exactly to the same extent, this reparametrization appears. And it was recognized, I believe, first by Sompolinsky and Zipelius some, I don't know, 40 years ago. And this is the reparametrization invariance for our problem. You notice it's not quite the same as you are accustomed from what SYK. And we know, so meaning that this slow part can be reparametrized. Of course, there is only one reparametrization that is the good one, but we know what to do to change physically a reparametrization. We know how to couple. And for the plastic ruler, it is every Friday of the week, you take your ruler, you bend it up and down, and then put it back on your shelf. And this makes the H hurry up a little bit, and it makes your system younger. So if you want to keep your ruler sort of young, you do that every week, and then your ruler will be always forever and ever, let's say, a week, a month old. So why is this? Because the bending, which is a shearing, couples to the reparametrization. So you see that reparametrization here appears, and it's quite physical. If you have questions on this, it's a nice
Yeah,
time
sorry,
to.
I have a very naive question. I just missed what these four different curves are. What is changing in these four curves?
So you take your system, you produce your system, and then you take a photo of your system at time t1 and see subsequent times, t minus t star, how things, the molecules move around, rearrange. And you see that there's a fast rearrangement, the vibrations, and then very slowly they creep and they move around. In a glass, things move around.
Okay.
Now you take the same ruler 10 times older, and you do the same experiment, and you will see, first of all, again, the vibrations, which are always the same, like you would have in a crystal. And then those rearrangements, the slow rearrangements where the system is trying to find its better optimum, happen at a rate that becomes 10 times slower. And then 100 times older system, you do the same. And again, there are these rearrangements that take place 100 times slower. So if you're considering this kind of rearrangements, they are taking longer and longer depending at which time you started after you produced your system, the age of your system. This, of course, is telling you that you're not definitely not in equilibrium. Something is changing. Although in the ruler, not much, you don't see much, but the experiments show that these have been done. You compress the ruler at a given time, and the way it creeps to a new size, these are tiny little compressions, the speed with which it does it scales with the age of the ruler, inversely with the scale with the age of the ruler, which is an incredibly mysterious thing, but this happens. Is it okay?
Yeah, I guess by age you mean just when it was manufactured. So,
Yes,
sorry, like
when it went through the liquid glass transition. So it has to be the moment where the plastic was molten and puff, the temperature was quenched to room temperature.
Okay.
So this is how reparametrization.
Also, in the in this slide here, it looks like maybe we could say here that like the eta has dimension 0 and the noise term it's like has dimension 1 or something. That's what this.
Yes, as soon as you see I use the integral, then this one has dimension 0 again when you do the integral. So okay. Yes,
the thing that's bothering me
so
is
they
that
have both.
If I understood right, the noise that you put in doesn't have that, like the xi correlator was just delta of t, and that doesn't have.
Yes, that. Exactly. But later on, if we consider periodic trajectories, then you are asking something about what happens at the end of the trajectory. So you are conditioning, and then the noise, even though it was conceived with delta correlations when you when you condition to something that happens in the future, you distort the actual noise. This is why you have to, in some cases, take it into account. In this case, no. So it's a question of causality.
Okay.
Okay, so now another thing that is important, another element is, if you plot a correlation and a response, like the ones I've been plotting, and you plot one against the other, you get a straight line, and this is known as the fluctuation dissipation theorem. It's exactly the thing that Einstein discovered that related the friction of water with the noise that the water was producing on your Brownian particle. So take my word for it, it's not hard to prove. It's an internal symmetry between your two correlators, if you are in equilibrium. And now when you do it in our case, where you're aging, I can, if I want, do a parametric plot of the integral of R against C, and something very, very strange happens. I get two different temperatures, as if it were two different temperatures. For the fast part, I get what I would get in equilibrium, and another temperature appears, another gradient which plays the role of another temperature, as if the system on its own had developed another temperature. This was a very big surprise. And where does that temperature come from? This new temperature that appeared, that the system has self-generated. It is out of equilibrium, so you can have more than one temperature. This is the particular way in which is out of equilibrium. These systems are out of equilibrium. And you can have more. You can have 3 time scales and 3 temperatures, and so on and so forth. And the time scales are nested one inside of the other. So those of you who are into SYK, you have 2 time scales. One is the order 1, of where the derivative has a meaning, and the other one is the infrared, which is the slow one, where you are neglecting or sort of neglecting the time derivative. Here you can have more than 2. So you can have one that is order 1, where the derivative is not negligible, another one where it is, and another one where not only the derivative, but the previous time scale is already negligible, as if they were, you know, Russian dolls. And this is typical of classes. You could even have an infinity of these. So all in all, what you get is several time scale, a temperature that has appeared through fluctuation dissipation in each time scale. The temperatures are the same for all different observables, but at a given time. So this is the picture which we call multi-thermalization, to give it a name. And you have reparametrization invariances, and moreover, you can, in some cases, put it in connection with the Parisi scheme, which was for equilibrium, but by indirect arguments, you can put them in relation, in the sense that the temperatures that appeared can be related to some parameters of this bizarre construction. Okay, so this is the picture that emerges, at least in mean field. And so let me play a little bit with reparametrizations and reparametrizations invariance. A game we like to play that I haven't seen in the literature of SYK, but I haven't seen it all, is to construct time reparametrization objects. Here it would be like a radius. So what I do is I take 2 times, a large one and a very much larger one, and I say that I'm going to construct a triangle with T1, T2, the correlation, and T2, T3. So I am looking at this triangle. So you see this relation, if there is a function that tells you how the triangles are made in correlation, it's a reparametrization invariant fact, this F. So people have tried to plot this F in a plot and then look at the fluctuations. And if reparametrizations are soft, you should move along these lines. And this is what you see in a real system. This is a direct way to see reparametrizations. It's as if in this picture of somebody moving in this tilted Mexican hat, I would be looking at keeping the radius constant, looking at the fluctuations around this thing. And of course, they would be like in the little red line that is hardly visible there. So, okay, this is a quick thing. Okay, so now comes the big problem. Okay, the system develops timescales. The system develops a different temperature, but only if they live at different timescales. So I have system number 1 that is connected to a heat bath of temperature T, a system number 2. And because I constructed 2 different systems with different parameters, they develop 2 different timescales, sorry, 2 different temperatures. But now I have a problem, because if I couple these 2 systems, I would immediately be contradicting the scenario that I said a minute ago. The coupled system will be having 2 different temperatures in the same infrared timescale. And I have said that you need to be at very separated timescales to allow yourself to have different temperatures. So how can this scenario work? And if this scenario doesn't work, then you can go all the way down to the Parisi ansatz and show it that it doesn't work either. So what happens? And what happens is a little bit of a surprise, is that when you couple the system, because of reparametrization invariance, timescales are soft. And the system is wise, so the fast scales that are in contact with the bath keep their temperature. The slow one keeps its temperature if the coupling is very small. And the other one shifts its timescale so as not to disturb this one. And it now lives as a third timescale. So what would have been 2 timescales that violate the scenario because you have 2 different temperatures coexisting there, the 2 temperatures have kicked each other apart and live now in completely different timescales. But how can this be if the coupling was, as I say, infinitesimal? Well, you know the answer. It's thanks to reparametrization invariance. If you have reparametrization invariance, as you know very well, those of you who do SYK, this allows you to shift around timescales at lower and lower costs. So you see, the whole scenario here can work, having temperatures, different temperatures only living at different timescales, thanks to the fact that time reparametrization allows them to move around so as not to step on each other's feet. So this is nice because it shows you how important it is even for this question, for this survival of the whole picture. For this, otherwise, as soon as you couple 2 different systems, they would immediately fall away from the scenario because they're not going to, by chance, have exactly the same temperatures at the same time scales. They don't, but the slightest coupling, and because of the softness of time scales, you can kick them and they move around. Okay, so now last, where the thing gets a bit closer to the world of SYK. So as I say, we want to count thermodynamic metastable states of the system, of the stochastic system. For the moment, nothing was quantum. Now, it turns out that, as I say, if you count the number of periodic orbits of period lifetime with their probabilities, the result you get is the number of metastable states. I cannot explain this very easily, but it takes half an hour on a blackboard. It's not hard, but you need some convincing. In any case, if you have a ferromagnet that has an up state and a down state, if you count the number of periodic trajectories of the system, it's a stochastic system, in a long time, it gives you 2, the result, which means that you have an up state with positive magnetization and a down state with negative magnetization. Take my word for it. It would take 20 minutes to explain this, but it's an elementary fact. So now we're going to try to go directly from a system that was stochastic to a quantum system between quotation marks, so that we get closer even to SYK-like situation. So remember, we started with a stochastic equation that looked like this. And people tell us that when you have an equation like this, the probability evolves through this operator. So this would be like the diffusion, and this would be like the Laplacian, if you want, but with a potential. So that the probability distribution evolves like this with this object, or I have just added artificially the potential this way. And here comes the interesting thing. The evolution of probability is guided by what is this thing. It's a change of basis, a Hermitian operator that looks very, very much like a quantum mechanical system. So a diffusion problem is like having an imaginary time evolution with this Hamiltonian. And this is why I kept calling temperatures TS, meaning stochastic, because now my temperature is not going to be this one. This is playing, the red thing, the role of H bar. And those of you who have seen supersymmetric quantum mechanics will recognize this. So the morals of this is, from a diffusion problem, you always can cook up a quotation marks quantum Hamiltonian, which you can sell as a quantum Hamiltonian, let's say. It's not related to any quantum process that I know, but you can construct one like this. And this process to do this is called Roxar-Kivelson, because they constructed models of solid state this way. They had some stochastic system, constructed a quotation marks quantum Hamiltonian, but from this one, they found a lot of properties. This is a valid quantum Hamiltonian, and it's called Roxar-Kivelson, but they didn't do it for a glass. Now, what is the amazing connection, and this is part of what I was saying about the periodic trajectories, is that if you look at your system, your stochastic system, which has metastable states in the sense of, you know, being there with your dynamics, this landscape is directly recognizable through the spectrum of this Hamiltonian. So the spectrum of this Hamiltonian, the low-lying states are concentrated around the metastable states of the original stochastic problem. And their lifetime is their energy, their eigenvalue. So if something lives forever, it has zero eigenvalue. All this to say that if your original system was a glass and you were doing the dynamics of the glass, then you have a lot of metastable states by definition of glass. And if your glass was a mean field glass, it has an exponential number of completely stable metastable states, all these little valleys I'm showing. For each one of these little valleys in the Roxar-Kivelson, let's say Hamiltonian, there is one of these states. And because the eigenvalue is the lifetime, if these are stable, their eigenvalue is near zero. The entropy at low energies of this system is the number of metastable states of the original system of that lifetime. So now I can count these by writing a partition function. Now a true quantum partition function. I'm putting this H, which I have now invented as a Roxar-Kivelson, if you want, Hamiltonian, quantum Hamiltonian. And now what measures the temperature, the time, sorry, which is the periodicity, because this is a trace, is my quantum temperature. So my quote unquote quantum temperature is the number of metastable states of my original glass. It's a confusing thing because the connection now I'm making between glasses and SYK-like systems is not through the partition function, it's through their dynamics. And through their dynamics, I am counting the periodic orbits, and through the periodic orbits, I get this Hamiltonian, which is the stochastic dynamics, and I get the spectrum of the operator that evolves the probability. So all in all, for any classical glass, through this Roxar-Kibelson-like interpretation, you get a strange liquid or a strange metal, because the many metastable states that by definition any glass has becomes many low-lying eigenvalues of the quote-unquote quantum Hamiltonian that I have constructed. So this is the closest I can get, because now we have the trace of the evolution operator. The quantum temperature measures the lifetime of the things there. Now that part I can show. So we have two elements at least: reparametrization invariance, which appears in a certain way and plays a role. And then we have this direct thing that shows us that ground state, zero temperature entropy is finite. And now this is, if I have 2 more minutes for amusement, I have seen the wormhole between two SYKs. So I asked myself, the wormhole between two SYKs is just connecting two SYKs, much like I was doing before, putting them together by a coupling. And for exactly the same reason that before, when I was talking about the temperature reshufflings, the system was very sensitive. You expect for SYK them to be 2 because they are free. You have 2 reparametrization invariants separately of the 2 systems. And of course, they can kick their elbows mutually and do things very easily because they're soft in that direction. So you do the same here. And so I just have class number 1, class number 2, which is the same, but it's a copy with another coordinate. And then I do some interaction with a mu that wants them to be together. So it wants that this copy of the glass is in the same configuration as this one. But you have many choices. So when you look at how this is constructed, you see energy term, this term, wants you to put the 2 glasses in the same state, this one and this one. So you want them to be in the same configuration. This is what the interaction wants. On the other hand, entropy, on the contrary, there are exponentially many of these states. So entropy doesn't want that. Entropy wants you to make a couple of any one of these states with any one of these other states. So there is this battle between the attractive term, which makes both copies want to do the same, and both copies want to do randomly different things. And when this happens, because temperature plays in favor of energy and, plays in favor of entropy. So at some point, when you go to 0 temperature, it's the blue curve that dominates. When you go to larger temperatures, entropy kicks in and plays a role, and you get a first order transition, just like when you couple 2 SYK models. The interpretation is different, but it is again a remarkable coincidence, I think. Of course, calling it a wormhole is a joke. I mean, there's no wormhole. Okay, so that brings me to the end. So the analogy, as I say, goes very far. I don't want to say that overstated, but it is quite surprising, I think. T equals 0 entropy is something you do have automatically. And reparametrization invariance, you do have, and it has always played a role. And only now we understand how important this role is. The whole solution of everything from the Parisi ansatz to the multi-thermalization relies on this reparametrization invariance. One thing that you have that you don't, as far as I know, have in SYK is that you can have more than 2 timescales. So you can have ultraviolet, infrared, super infrared, and super infrared, and things like that. I haven't seen that in that world, but in glasses, this happens automatically since the beginning. And if you want to see the relation with the Parisi ansatz, it has to do with this nestedness of the blocks. This is an important disclaimer. The group that survives when you choose your reparametrization is not an SL2 group. It's a poorer cousin. It's some. It is something like just stretching, translation, and there is if you want a symmetry between the fields, but it's not SL2. So things that depend crucially on SL2 will not be reproduced. Perhaps the Lyapunov, which we haven't calculated, is not going to saturate the bound if that depends on the SL2 being SL2 and not only on reparametrization invariance. So reparametrization invariance you have, zero entropy you have, but the specific things that require that residual group you don't have. So those, as far as I know, don't have a counterpart in glasses, not that I know at least. And this is indeed a difference. So that is more or less what I wanted to tell you.
Okay, thanks, George. The floor is open for questions.
I have a question. This is Steve Schenker. Does this sum over periodic orbits giving the number of states, is this at all related to these quantum chaos sums over periodic orbits?
No.
No.
No, no, no. It's not directly, no. It's just that when you sum over the periodic orbits, you are with noise, no? You're yeah. Calculating a trace, and because you're calculating a trace, let me see. Because you're calculating a trace, you are when you're doing this trace here, you are in fact estimating how many levels you have that are smaller than this T star.
Mm-hmm.
So, and now the connection that is a theorem is that states that are low here, eigenstates of this operator, are in a one-to-one relation with the valleys of your original problem. So that's the relation that counts. But it's not as in Gutzwiller stuff, not that I...
Mm-hmm. I see the paths are constant in imaginary time sitting in the different valleys.
Yes, the thing is that, here you're using imaginary time indeed, and the things that survive for long have to be low eigenvalues of H. So you see already that they are the metastable states. Now you could ask me, what happens if I put an I here? If I put an I here, I don't get anything that I can associate with the original diffusive system. It's mm-hmm. just, it would be quantum, but yeah.
Thank you.
Can I ask? So I'm trying to I was trying to understand this thing about nested timescales and nested temperatures.
Yes.
Okay. So would the analog in the Schwartzian or SYK theory be that if the Schwartzian action is the Schwartzian of T and U, then one temperature is corresponding to the T time scale and one temperature corresponds to the U time scale?
It's more like imagine that you had a Schwarzian, but it would be in that scale, you would have several fields. And what was an original symmetry of those fields in the ultraviolet has chosen a different subgroup in the infrared. And then if there would be a super infrared, these fields would be related via yet another symmetry. So it's a kind of, it's a strange thing that happens.
Sorry,
But
so perhaps my question, I think you're answering a more, slightly more intelligent question than I was asking. So even before you couple these two systems, right?
yes.
So there is just there are two timescales and two temperatures.
Yes.
And I think you were saying that the SYK theory also has the same phenomenon of two timescales and two temperatures. Is that right?
No, to timescales, no, I'm not claiming. Here what happens is that timescales are labeled by their temperatures, and if they are labeled differently, they don't want to live together. They don't want to, and thanks and only thanks to reparametrization invariance is that they can kick each aside, let's say.
I see.
Which seems almost like special pleading, no? But it is true.
I see. And like the time scale as a function of temperature is determined dynamically. Is that the point?
So it depends on the situation. The time scale is evolving with the age of the system in the aging regime. So the separation of timescales is due to age. However, you can put the same system by making, and this has been used in SYK too, you could change in some cases the disorder with time, like has been done in SYK. So if you have a system like this one, you change the couplings very slowly, and then you regularize everything, and that is the parameter. The rate of change of the disorder is the master of the whole thing, just like beta is in SYK. And then you have no more aging, and you can work directly with time differences and everything. Much less physical, but much easier.
I see. Thank you. Thank you.
You showed these equations for the aging dynamics, the C and R. Are these the same equations somehow that we get if we study the partition function of the Roxar-Kivelson-Hamiltonian using collective fields, or is it?
Okay. Yes. I think I had them. If you do a trace, which is what you normally want to do, of the Roxar-Kivelson one, you get essentially the same equations. There is a D also, because D is no longer trivial once you close the trajectories. They are nasty, but they are essentially like these. Yes, it's a three-component thing. Yes.
And are the solutions that are relevant for counting the states, are they time translation invariant?
Yes.
The solutions you showed here for aging, I guess, were not, right?
No, indeed. But the ones, yes. And those we calculated many years ago with Giulio Biroli, and yes, they are time translation invariant, yes.
And is the important difference there just the boundary conditions, or is it the extra term, or the difference in the structure of the equations? Why is it?
No, it's the boundary terms and what you call, let's say, quantum temperature, which is no longer the temperature of the original system, is just the lifetime that you are asking to calculate how many states there are, because it's the periodicity of the thing you're calculating. So when you demand to know how many states there are of a longer time scale, you are changing your beta. What you would be your beta in SYK, the solution stretches in a less interesting way than SYK, because it's not SL2, it's just stretch. It reparametrizes, and it gives you a new number for the number of metastable states of this new time scale. The more you are picky about the time scales, the longer you want them to live, the less there are, of course, because it's easier to make shorter ones.
Is that Roxar-Kivelson model, like, is that, for this glass problem, is that, can we think of that as some bosonic SYK model? Like, how close is it?
it is a cousin that has reparametrization invariances, that has ground state T equals 0 entropy. I don't think it has linear entropy with temperature, and its residual group is not SL2, but some stupid translation and stretching group. It doesn't have the third generator. So it's a poor cousin from that point of view, of which we know a lot of things, let's say. Now, the beautiful thing would be that someone discovered that SYK is a stochastic system or comes from one. But I don't think that life is so good.
Well, but in that formulation, it's not a stochastic system. It's just some quantum. We can think of that thing as just a quantum Hamiltonian for some bosons with some kind of random potential.
Absolutely. And Roxar Kivelson, they were doing other stochastics problems and treating them as quantum. As soon as they perturbed them, they stopped to be coming from a system. They were just quantum without coming from anybody stochastic.
Okay, I have two more questions about that. So one, is there an effective action for the little h that you can derive for the, let's say,
this has been attempted, and I'm convinced it has been attempted, and the people who did this picture, I'm very short on references, but you can find them all in the, so, oops, people who did this, just have a second. Yes, people who did these plots, which is Chamon, Kenneth, Culiandolo, Castillo, there's a lot of papers. They were trying to get an effective actions. They wrote one, and they were a bit overambitious because they wanted to do it with space and time, and they didn't put the time part, they put the space time. So it's a problem because we know that there has to be a time, but they were aware that something like this is what needed to be done. I think that it was a right idea, their checks were nice, but it's not, the project is not complete. But you will find interesting stuff. For example, these plots are very cute. They show you how the system wants to live along this is the radius for you here, so to speak. And these are reparametrization invariant times, the green line, and changing reparametrization is moving along, and you see how the natural fluctuations, statistical fluctuations of the system want to go along that line. Like they're telling you, I am soft.
I see. I guess without the SL2, you would guess the action would just be like h dot squared or something.
Something like that. Although the problem that stopped us from, I mean, we were aware that this was necessary long ago, but the problem is that this nuisance of it being aging, and so that we were not calculating traces, but we were doing aging, then it meant that it wasn't all in terms of time differences, and then it becomes really, really horrible. However, so that was an open problem, has been an open problem for ages. Maybe now reading at your literature, we'll end up by doing it.
Okay, thanks a lot. I see Emil has his hand up, so let me stop asking.
Yeah, I just wanted to ask a question about this breaking of SL2. So the equations at some point that you wrote down indeed bore a remarkable similarity to the effective field equations that you write down for SYK. So can you see in those equations where the breaking of SL2 came from?
Well, first thing I can say is that if you want the power laws that appear here are not a half or anything that one can associate with reparametrization. So nobody has ever found a third. When you look at these decays, another operator other than the silly ones like translation or things like that. But the third generator, the nonlinear one of the Virasoro algebra, nobody has found a thing that leaves them invariant or something like that, other than the obvious ones. So for the aging case, and for the trace case, as Douglas was saying, it's flat and there's no need. So it's less rich, I think, than the situation. Maybe there are other symmetries. If I have to tell you what the symmetry is, that is the residual symmetry, it would be something like the group of reparametrizations of superspace in one dimension that leaves the super Jacobian invariant. It's a mouthful. I don't know. I asked friends if this meant anything to them, but nobody, it never rang a bell on anybody. So I don't know.
Okay, thank you.
But it's not just translations and super translations. What is the dimension of the?
No, there's a bit more. There's a bit more. This has not been really studied, but there is a bit more, and it's a bit more than translations and super translations, now, not all of them have an interpretation from the original point of view. So this has not been, I really don't know. But I do know that super deformations, that you can write the reparametrizations I wrote as a transformation in superspace, keeping, so you stretch the fermions and the thetas and the times in opposite ways so that the volume is maintained, and everything is invariant with respect to that. So it's either a symmetry on the coordinates if you look at it from the point of view of superspace, or a symmetry between fields if you just write the components. But I think that the problem is poorer from that point of view. I mean, there is no obvious.
It seems kind of surprising. Like I would have guessed this RK Hamiltonian, you would have had the conformal solution, like I don't know, it's some SYK like bosonic model. Why not have that?
Yeah, one should look in detail to that. But the equations are what they are. This is. They are okay. I mean, these ones.
What is the reason for the supersymmetry? Is it somehow related to preserving the probability, total probability?
Yes, preserving the probability, and also temperature appears as a supersymmetry. The fluctuation dissipation theorem and the temperature, this is known, can be written as a supersymmetry. This is even, I don't know, in Sinjostan's book you can find. And the fact that the system in the low scales, in the slow scales, chooses a different temperature, it's like changing the supersymmetry generators that are relevant there. So it's a kind of a symmetry breaking. It's nice, but of course nobody, I mean, this is not the kind of thing you can, I mean, you don't put data in many articles in StatMech if you want to get read.
Are these, I mean, sorry, but are these aging solutions? Is this something we should be looking for in SYK? Or do you think?
So somebody, maybe you asked this in Santa Barbara, and I actually wrote what would be the analog. Unfortunately, I could look for it, but I can also tell you in words. If you did the following in SYK, I don't know, I don't think it has a big importance, but let's say you did the following. Somebody told you what is the ground state of your system, the really lowest state, and you put that to the left. And then you start from a random state to the right, and you evolve with imaginary time, what you would call imaginary time, that would be the analog.
Wait, sorry, we would call it imagine. Okay.
So it's without an I.
Yeah.
Without an I. So let me, if you wait for a second, I wrote it once, so I can find it. Just a second.
Right. Okay. Okay. Yeah, I remember you.
Yeah, but I did it a bit better this time. Yes. So, oops, just a second. Here you have it. Now let me, can you see this?
Yeah. Mm-hmm.
So if artificially, init is anything initial, but 0 would be your ground state. Now imagine that for some reason you decided to calculate this. I don't see which reason could lead you to do that, but if you did want to calculate this would be aging. So you see you are evolving towards the ground state, but because you have so many states and they are so degenerate, this takes forever, because e to the minus th is not very efficient in projecting you to 0 because it is highly degenerate. So this is, by the way, in the paper I was advertising in the first transparency. So this would be what for you would be aging.
Mm-hmm.
If you can see it, yeah.
So can I ask a very basic question? So is aging basically a definition of spin glass phase, or it is?
I would, from my bias point of view, that for me, it is the definition of what a glass is. It is something that is forever looking for equilibrium, and it doesn't find it in any time that you have. Sometimes it does. Whether it does eventually or not, it's an open question always, and we will not know. But about the real ones, no.
Mm-hmm.
But this for me is what is a glass.
I thought I heard somewhere that SYK model doesn't have a spin glass phase.
In the sense of being replica symmetry breaking for the statics, that's true. But you see the analogy.
Do you think that this is somehow related one-to-one or not? This, yeah.
So what I can
symmetry breaking in presence of aging, or is this an open question? Yeah. What is the relation between this?
So what I can, what I can say is take any glass you like. So by definition, something that has very slow dynamics. The dynamics is classical and in stochastic, and is generated by an evolution operator. Now, write it in its Hermitian form and show it to a friend of yours and tell him that this is your quantum Hamiltonian that you like, although it didn't come from there. That thing there, the one you're selling as a quantum Hamiltonian, has ground state entropy, reparametrization invariance, and all those things, but not, as far as I can tell, an SL2 thing. But it is a strange liquid. But the connection is not direct. It is through the dynamics.
Let's see, if we take this expression that you wrote there, C aging,
yes,
and suppose we multiply it by its complex conjugate also, then we get another copy of that thing with now the init state is the bra, not the ket. And suppose now we average that over the initial state.
Yes, but
that just becomes an ordinary 4-point function, right?
Yes, but you need to here, because you're using imaginary time and you want to go all the way down. What dynamics does is zero is the true Gibbs-Boltzmann equilibrium. So the system is trying to get down there. So I never found a way. What you could do perhaps is starting from a state at a given temperature, and then instead of zero, using something with an extremely lower temperature. So then what you would get is something that is slowly stretching its time scale from an initial one to the one corresponding to the lowest one. Mm-hmm. So then that could be a kind of variant. Instead of using the true ground state, using an extremely low temperature situation here in the zero, no? Instead of the zero. But of course, this is a bizarre object. You know, I put it here so only for purposes of, let's say, comparison. I don't see where this would arise in a quantum, as far as I can see.
Is it self-averaging over the choice of the initial state?
Yes. If you're not perverse, of course. I mean, you're not supposed to, you take a random one, no, or relatively random. Yes. Everything is self-averaging. To the exact extent that things are, the maths of SYK up to that point is very close, really very close.
So are you saying that if you're at low but not zero temperature, then there's some issue that it's still difficult for SYK states to hop around and relax?
Yes, but this relaxation I'm using is a very, it's not the real thing, no? It doesn't have a true quantum anything. So this is just a bizarre way of using imaginary times. I just write it because this appears naturally when you interpret the thing as a stochastic thing. Once you want to sell it as a quantum Hamiltonian, this doesn't have any particular sense. Just as the true evolution with an I has no sense in the stochastic context, or not that I can say.
These type of correlators actually, I think, were studied in SYK, well, in the paper by Maldacena and Korkulu.
Maybe, I don't know. If they were, it's interesting because you see the difficulty. Take this one. The system would like to project down to its lower eigenvalue, no, eigenstate, but it's hard for it to do it because there's a lot of quasi-degeneration at the lowest level. So it's hard from this e to the minus th to project you to where you want to go. So this is why it takes infinitely long. And it's a way of probing if it could be done in some way, but of course you don't know zero, I guess. But it would be a very nice, elegant way to probe how the levels are, let's say, no? I think.
And the operator A, we should think it's like one of the fermions? Or?
Well, with bosons, you can do with one. With fermions, we'll have to use a pair, I guess. But yes,
I said you don't want A to be a fermionic.
Well, in the cases that we didn't do fermionic, but you could also have stochastic systems that are represented by fermions. We never tried it here. So you can do a Rox-Archibaldson fermionic being fermionic too. We didn't try it here, but basically A can be any reasonable operator that can have an expectation in your problem.
Okay.
Okay, are there other questions? If not, let's maybe end the formal session here. We can thank the speaker again.
Thank you.
And stop the recording.